Good afternoon, everyone. Thank you. And thank you, Dr. Milas, for that wonderful work you're doing. And we are so excited by the collaboration that we have with you and Dr. Peterson and everything that Trent has done to spearhead and build that relationship. It's a lot of exciting things that we're going to be doing in the future. So I'm going to give you a crash course here to SAM, which is a space analog for the Moon and Mars. And this is a habitat analog. So just in brief, analogs are places that we practice procedures, technologies, techniques before we go do the real thing. You can think of a swimming pool as an analog for learning how to swim before you go to the ocean. And there's a long history of analogs, specifically by NASA. Our own Professor Gene Shoemaker, back in the 1860s, used Meteor Crater, Arizona as an analog for Apollo astronauts, where they trained in using their spacesuits and rovers and geology tools prior to actually going to the moon. So even here at the University of Arizona, we have a wonderful history with this kind of research vessel. Does that work? It's not working. Hold on. Oh, there we go. There we go. Okay, so this is the test module. This is built by the Biospherians back in 1987. At the time, this was the world's largest human-in-the-loop closed bioregenerative life support environment. It is a 400 square foot vessel, completely hermetically sealed and pressurized from the outside. The longest stay was by Linda Lay, one of the original 8 Biospherians. She was inside for 21 days without any outside air, food, or water. Even her human waste was recycled internal to this facility. So it was an excellent experimental test bed for what would then become the Biosphere 2, the much larger 3.2 acre facility. So in 2021, fast forward about 30 years, Trent, Tresh, and I, this is our very first photograph, our very first day, came to this facility. It had been abandoned for about 25 years, and we had a lot of work ahead of us. So this was also in the midst of COVID, so we were working as carefully as we could, mostly outside with our masks. And over the course of the last 2.5 years, we have completely refurbished and renovated this structure and added on, as I will show you. I'm going to take you just through a brief few photographs to give you a sense of the physical labor that's been involved in the construction of this facility. There we go. So we've done a lot of work with metal, with rubber, with plastic, with glass. We've, as I said, completely refurbished this facility and given it new life. We've had over 35 volunteers from around the world in the last 2.5 years, 35 volunteers and staff who have been diligent in their effort to do not always fun work to bring an old building back up to speed. This is in June, the end of June 2021, just 5.5 months after we initiated the renovation of the facility. And this was our very first pressure test, 5 people sealed inside for 4 hours. And we had several monitors, CO2, carbon dioxide, oxygen, relative humidity, temperature, and pressure. And the next graph just shows our very first data accumulation or acquisition during that pressure test to demonstrate that we had had success in able to maintain approximately 1/20th of a PSI. It doesn't sound like much, but even at 1/20th of a pound per square inch, it's still 180 pounds of pressure on the windows and about 150 pounds of pressure on each one of the pressure hatches. So it's still significant and enough to cause some people's ears to pop. It definitely gives you a sense of being inside of a real spacecraft or habitat. So then the construction continued for another 1.5 years, everything from placing shipping containers on concrete piers to drilling and more welding and more cutting and more grinding and tearing off the roof of the old rainforest greenhouse in order that could become our indoor Mars yard. As far as we know, it's North America's, or will be North America's largest indoor Mars yard at 6,400 square feet. So we did all the insulation ourselves, all the welding, some of the welding ourselves, some with the help of the welding facility here at U of A and the experts therein. And this is, again, I fast forward through about 2,500 photographs in 2.5 years of work. And this is an artist rendering of the final layout. And I don't know if I have a laser pointer, but I'll generally point. On the left-hand side, we have the original test module, and then we've added on a 20-foot shipping container pointing to the west, and that is our engineering bay. And then the longer 40-foot shipping container is the crew quarters that contains sleeping area, kitchen, common area, bathroom, and then the airlock. And the airlock was actually built by the Biospherians and again recycled. We took it out of the basement of Biosphere 2 about 1.5 years ago, and we're able to seal that to the side of the shipping container. So the principal science objectives, and by no means are we limited to these are the ones that we're interested in, are the transition from physiochemical or machine-based to bioregeneration or plant-based life support systems. Everything on Gemini and Mercury and Apollo, Space Shuttle and ISS is all mechanical. It's all physiochemical or physical chemical life support. So we're using chemicals to adsorb the CO2, and then we're heating those chemicals and releasing the CO2 to space. And we know that for long duration habitats on the moon or Mars, we have to have bioregenerative. We cannot rely on a continuous shipment of these costly and often heavy and sometimes toxic chemicals or elements to the moon or Mars in order to sequester the CO2 that we produce as living, respiring creatures. So we will be the first people in the world to demonstrate. We're going to walk into this facility with a long duration mission, maybe a 90-day mission, with seeds in our pockets. And we'll initially be reliant upon a CO2 scrubber, similar to the one on the ISS. And we have Paragon to assist us in the design and construction of that. And then we will grow those seeds into mature fruiting plants using our hydroponics bay. And we'll see a reduction in the use of that CO2 sequestration system, the mechanical system, because the plants themselves will do exactly what they do every day for us here on Earth. As they mature, they will begin to offer their services as living organisms. And that's the first step towards that long-term bioregenerative process. Very exciting work. And we have a PhD student named Attila from Peru, who is part of the University of Arizona now, and will be conducting that first effort, hopefully within the next year and a half. We also learned how to close air, food, and water cycles. That began with the very first mission that concluded last week, and I'll talk a little bit more about that. A study of the microbiome. We have an exceptional number of professors and students here at the University of Arizona that we can call upon for that study of the microbiome. As most of you know, we've become much more adept at understanding, although not fully understanding to any degree, the depth at which the microbiome plays into our daily lives, everything from our personalities to our digestive systems. And we want to really understand that transition of the microbiome as we have a transient crew moving through our space, either a few days at a time or a few weeks at a time. I really don't like staying in hotels anymore once I've learned how much the microbiome of the previous tenant affects my microbiome. It's a little bit scary. So I prefer to sleep in my tent. We will also be testing pressurized suits, tools, and procedures, which again, we conducted just last week. We believe we are the first institution in the world to demonstrate a person who is blind conducting an EVA in a fully pressurized spacesuit in a simulated Mars terrain, our Mars yard. So she was able to navigate the terrain using her cane. And for any of you who have ever been inside of a pressure suit, probably not many, she was not only blind, but also deaf. You cannot hear the outside world when you have the air moving through your suit and you're in that pressurized space. So she was fully reliant upon the tactile feedback of her cane and trusting the communications over the radio with our ground support team. It was a phenomenal event, and we're very, very proud of what we accomplished on our very first set of EVAs. And of course, advanced computer model simulation, monitoring, and management. This is CMOC. Typically, this is its own hour-long lecture. This is a computer software environment that my team has been developing since 2017, initially at Arizona State University, and now with some funding from University of Arizona. This is both a agent-based simulation of a mechanical and plant-based life support system in a closed environment with humans in the loop. But we also have CMOC Live. And CMOC Live was running during the first mission, we'll be running for the second one. It's capturing all of that data such that we can take the data, feed it back into the simulation model, the agent-based model, and further improve that in the proper scientific method. Collect the data, improve the model, predict. Collect the data, improve the model, predict. And we're already moving down that path. So I'm going to take you on a quick tour of the facility as it stands last week. This is our airlock. Again, it's a fully functional airlock. This is not pretend, it actually works to that 1/20th of a PSI. There's a wonderful rush of air when you pressurize or depressurize. Last week, we moved 47 people in succession of 6 people at a time through the EVA as part of the Analog Astronaut Conference. People were thrilled. It was certainly the first time in their life they'd actually entered or exited a spacecraft through a proper airlock. So there's our spacesuits, which were manufactured by Smith Aerospace Garments out of Portland, Oregon. This is our crew quarters. Eventually, they will have private sleeping pods. We weren't able to get those done in time for the first 2 missions, but they can move their beds around and sleep in different places. They're lightweight foam. So we have the full amenities of a kitchen. We've got spices and dehydrated foods. It's all vegetarian diet, bread maker, rice cooker, Instapot, microwave, convection microwave oven, and water kettle. And we bake a loaf of bread for each team 1 hour before they enter, such that they have the wonderful aroma of bread as they enter. And it turns out the first team was baking 2 loaves of bread a day. I think that's pretty much what they lived on. We are also taking all of our inedible biomass, meaning the food scraps, the broccoli stems you don't want to eat, and we dehydrate it in a commercial dehydrator, and then we grind it up in a NutriBullet and feed it to mycelia, playing off of the work of recently graduated Dr. Sean Gellenbeck and his work with Joe Coelho. And so we have already sprinkled our first teams, our first crew's inedible biomass into mycelia, and we'll be inoculating those mycelia soon, such that they can produce edible protein for the second team. And we have a beautiful bathroom. If I do say so myself, it's actually the most important part. People are always scared about what does the bathroom look like. And this is an RV, off-the-shelf RV toilet, which just happens to hold pressure. So when you flush, it's just like being on an airplane. You get that wonderful rushing noise as both your waste and the water exit the vessel. At this point, that is the only thing that leaves the vessel. Eventually, we will work to actually contain and retain and reuse the human waste as well. All of our water has 3 stages: white for potable, gray for gray water, and black for wastewater. We're capturing all the humidity from the breathing of the participants and the plant respiration in gray water buckets and recycling that water 100%. We also have an ADA-approved fire detection and alarm system that was installed with assistance from the U of A Fire Marshal. Absolutely beautiful system, $20,000, 3 weeks to install the thing, but we are now ADA compliant, which is fantastic. This is just a quick view of the interior of our airlock door, our engineering bay. A limited number of tools right now. We have a scientific scale, we have a 3D printer that's going to be built by the second crew, we have a microscope and some basic tools. And again, CMOC Live, which is collecting CO2, oxygen, and a number, about 11 different variables that's collecting in real time. And that's interesting. Huh. Okay, I don't know what happened there. I've never seen that happen. Anyway, it looks like my PDF is a little bit messed up. So this would be the carbon dioxide and oxygen levels throughout the first team. We have resolution such that we can actually tell you within 5 minutes of when they wake up, when they eat breakfast, when they're gathered and talking or laughing. I can tell you when they're sleeping just by watching their CO2 levels. It's that accurate. This is the original test module, fully refurbished. And this goes down into the lung. Won't have time to go into the physics of the lung, but this is the original pressure regulation system. That is a 4,800 pound sheet of steel floating on a cushion of air and providing the constant pressure for the entire facility. And that's one of our first crew members meditating in that space. The acoustics are just gorgeous. So all the teams end up playing instruments and singing in there while they're in HAB. We have 6 analog pressure monitoring systems called MagnaHelix. Our maximum pressure is 1.5 inches of water. And when we go on EVA, they are in fact breathing air from within the HAB through an internal compressor and a 100-foot umbilical cord that was set up and configured by Trent Tresh. And a quick view of the outside. We are actually registered as an experimental aircraft with the FAA. You can look up N1987B. That was a strong contender for, of course, 1701G for, I can't remember how many times Captain Kirk blew up the Enterprise, but we decided to go with something a little more local. And this is our first team and my crew, my present crew behind them. And this was the media event. We've had incredible support from the media. We made international news within a few hours of the first team entering and then exiting again at the end. And on the right, Linda Lay, one of the original 8 Biospherians, was present to welcome the team and to pass the torch to the next Biospherians. And this is Sherry, who I spoke of earlier on her EVA. So a bit of a timeline from 2018 till now. I've successfully raised, with the support of University of Arizona, Tech Launch Arizona, Kim Patton, Tim Swindle, and Elliot Chu, and John Adams, and Cherry Murray, and Joaquin Reyes, we raised approximately $300,000 to date. We have $1.5 million committed from the Arizona State Congress, which should be appropriated or delivered in July. And my closing text, which I won't read to you, but thank you. Any questions? Yes, sir. So the question is, how much do I know about the mycelia? I know nothing. That's the job of my staff, and so Sean Gellenbeck is certainly more aware of that. I do my best to keep up with, that's why I have experts. So I can. So the question is, do we understand the different species? Yes, we have 3 species designated. I don't know the genus or species names, I apologize. But we do have 3 separate species that, from what I understand, provide different fruiting bodies if we allow them to go to the fruiting bodies, which can be a hazard if they produce spores. So we're probably going to keep them in a non-fruiting state and rely upon the mycelia, the root structure itself. But those 3 different ones, if I understand, can be used in succession, such that the first one eats more of the macro elements, the second one eats the finer elements, and the third one consumes the finest elements, breaking down, for instance, straw to something. That's as far as I know.
So, sorry to keep asking. So, what kind of time cycle is all this happening on? All this successive process?
In a matter of weeks. It's a matter of weeks. So the teams. That's why the first team didn't enjoy the fruition of their own inedible biomass, but the second team, if we time it right, should be able to see some of the value of the inedible biomass contributed to the mycelia from the first team. If these teams were in more than 6 days, which is the ultimate goal of 2, 3, 4-week missions, they'll definitely see that full cycle from beginning to end.
Yeah. Thank you.
Yes, sir.
Missing all the graphics.
Excellent, good question. So what are our first generation goals and our long-term goals? First generation goal was not to die of a heart attack in the process of building this, and we succeeded. We have a long list of our stages of development, really a product roadmap. Our number 1 goal in that first 6 months was just get it pressurized again. We had to patch 12 holes where the rats had chewed through the rubber over the years, and we got it pressurized, we got it working. And then the second set of goals in phase 2 and phase 3 was to extend the pressure vessel and retain that pressurized environment, the hermetically sealed environment, and we were successful in that. And then to prepare an interior space that was comfortable, healthy, and safe for the crew, such that they could be in for multiple weeks at a time and actually live a full life, and we achieved that as well. The next stage is to build a CO2 scrubber, a swing bed CO2 scrubber, such that we can capture the CO2 produced by the humans, capture it, and then release it again to the plants, and integrate a hospital-grade oxygen concentrator, such that we can then capture the oxygen and provide it to the humans. And we're hoping to do this entirely with passive solar, which would be really, really cool. That's our next design over the summer. We also have a full mission control center, a 1,500 square foot building we'll be renovating this summer, such that the teams can be in both the habitat analog and run their own mission control out of a NASA-like facility. And there's much more, but we don't have time for it. Thank you, appreciate it.